Okay. Hello everyone. We are just about to get started. Apparently Google doesn't believe that I've actually started, despite Google believing it is 6 o'clock. One of those strange things. But that's okay. Today, we are continuing on with Theano, and we're actually going to build a neural network today. Finally, takes forever. Last week, you might recall, we did some multinomial logistic regression to classify digits, essentially using every pixel value as one of our features, and using gradient descent to climb on that and get a decent model with some amount of predictive capability. Now, however, one second. But now, there we go. Sorry about that. Now we're actually going to build a neural net. And I've actually got it running right now. I got that working just a few minutes ago, and I'm going to let that keep training while I sort of go through the tutorial on what the heck is this neural net. And that way, hopefully, it'll be at some decent point by the time we're done. So we're still at deeplearning.net/tutorial, and we're doing the multi-layer Perceptron. So the Perceptron is sort of the very, I don't want to say very first, but one of the earliest models of a neuron, I believe back in the 40s. I'm not actually 100% sure that this tutorial is using classical perceptrons, but that's what it's called. So before, we had sort of a layer of inputs, and we just had a layer of outputs. So we just had weights going from each input to all the possible outputs, so that each pixel in our image was in fact an input. Each pixel had a weight for every possible digit. It's like, well, this pixel is very important for ones. It's very, if you have a lot of dark in this pixel, that means it's more likely to be a 1. Or if you have a lot of dark, maybe that means it's less likely to be a 1. Whatever. Now, however, we're going to have a layer in between our basic pixel feature vectors and the outputs. So these are just going to be intermediate values that we're going to end up computing. And the way that you do this, you have your, excuse me, you essentially pretend that we weren't going outputs to digits, we were just going outputs to whatever this intermediate layer is, this hidden layer. So you still compute this like weighted sum of all your pixels. You've got some weight attached to each pixel for each node in our middle layer here. And this gives you some value. And then what the neuron does is it takes it and it transforms that. It puts it through some other function. In the original Perceptron, I believe it was the heaviside function. Essentially, it was on or off. If you met a certain threshold, it would output a 1. If you didn't, it would output a 0. These days, you'll see all kinds of different activation functions. I believe in this example, we'll use what's called a sigmoid. And that's essentially, it starts low in X, slowly curves up, and then goes back to slowly reaching its way towards 1, but never quite getting there. I believe that's correct. Let's show you guys a picture. Sigmoid function. There we go. That's Wikipedia. Yeah. Oh, that's logistic curve. Is that right? Various sigmoid function, various functions that are and are not sigmoids. Yes. So it's got a shape like this, and that is sort of look like popular as an activation function of artificial neurons. Hey. So if the weighted sum is pretty small, you'll see we'll get a value close to 0. If our weighted sum is pretty large, we'll get a value close to 1, and if it's in between, it will sort of scale in this nice way. The reason we use the sigmoid is that it's conveniently differentiable. Because the way you're actually going to assign these weights is through something called gradient descent, which I'm not going to get into, really. For this purpose, just all you need to know is that gradient descent, or stochastic gradient descent, is a way to iteratively climb on your weights. There are some good lectures on YouTube if you search gradient descent or multi-layer perceptron even. Those will really help you understand that better. They help me just see, oh, that's what they're doing. And it's sort of every time you get an answer, your net gets an answer wrong, you can propagate the error back through the whole net and update those weights accordingly with some learning rate and the derivative with respect to that error. So that's why the sigmoid is often very popular. It's easy to compute the derivative. When you're using Theano, however, you don't actually have to think about that. Theano calculates the derivatives for you. That's one of its nice features. Okay, so what was I talking about now? You've got this hidden layer. So you've got all these weights from your inputs, your pixel values. Remember, we're classifying digits. They go into your hidden layer. All of the, let me just, suppose you had just one unit in your hidden layer, one node, just for the sake of argument, say. Then you're going to get a weight from every single pixel value going to that node times whatever the value of the actual pixel layer is. You sum up all those numbers, all the weight times the value numbers. You shove it through the actual neuron, this sigmoid function, so you get out some new number. And then you send this value to sort of every output layer node. So you take, and now, yeah, you send that to every output, just like you sent the inputs to this node. Now imagine that you've got a whole bunch of nodes that are hidden in the middle. All of those are getting all the pixel values with different weights. And now you're sending each of those new values you've computed by shoving values through the neurons into the output. So you can think of this as covering up now the input layer. Suppose you've got some mysterious intermediate values that someone has told you these are important features I've extracted from the image. Now you're doing MNIST. Now you're doing logistic regression just like you were before. So the catch is this hidden layer in the middle. When you're doing the computation, you, the user, are probably not going to see whatever this hidden layer is. And so if you have at least one hidden layer, this is called deep learning or deep neural nets. In a net such as this, you might say, well, that has 3 layers. Often, like, the first layer is sort of free. You need that. So really, this is considered like a 2-layer. But one of them is hidden. And what's really interesting is that if you have a hidden layer, this is enough to make your multi-layer perceptron or your neural net a universal approximator. So you're not just approximating linear things anymore. If you have enough nodes and you spend enough time training it, you can just sort of memorize the data. You could approximate anything, any function. Which that has some nice properties. So you're going to notice a catch here. Before, we were estimating a handful of weights. We were estimating a weight for every pixel for every digit. So that's 728 or 700 and I can't add 784 pixels times the 10 digits. So like 7,000 or 8,000 some parameters. Which is a lot of parameters, but isn't the end of the world. When you throw in this hidden layer, now you've got those 784 parameters, plus 1 for the bias from every, there's one more input, the bias, that's right. Now you have that many weights times however many hidden nodes you have, which in this example you're going to have 500. So that's a huge number of parameters. And every one of the outputs of the nodes of the hidden layer has to go to every digit. So there's number of the nodes, 500 times 10 more. So there's a crap ton of parameters that you're going to be estimating. So this takes kind of a long time to estimate all these parameters. and it's going to take a lot of data. That's sort of one of the things to think about when you're trying to apply neural nets to a problem. You probably need a lot of data, and you need a powerful computation engine. I'm using a GPU on my local machine. If you don't have that, I might recommend smaller size problems, and if you're dead set on using neural nets, go for it. But not every problem needs a neural net. It depends on the scope of the problem. All right, how's this going? I'm an epic like 79 of 1000. So that's the multi-layer perceptron or artificial neural network or deep neural net. That's what we're looking at right now. Again, you've got the same pixel inputs, the same digit outputs. You're just computing a whole crap ton of intermediate values, and you're assigning weights. You're climbing on the weights to build up those. And you include your bias vectors all the time too. One of your hidden nodes will just be a bias vector as well. So you'll always send a 1 to all the outputs just to make sure you get that. And so the idea is you're sort of capturing some other sets of features. All right, now what are we going to do here? I'm not actually going to type all this in because I looked at this tutorial yesterday. It really is just a lot of typing. It is helpful to understand. It was helpful to type it all in and like make myself think about it. But what we want to do is screw around with this thing and see what happens when maybe, I don't know, we take out a lot of the nodes in the middle, or we add another layer. If you have one hidden layer, why not two? Sometimes that's better. And our goal here is to help to explore, do that, and to see how easy that is. So this particular page helps you build some of the machinery in Theano for easily building layers of neural nets. Okay, so let's look at this function. Formally, one hidden layer MLP takes you from RD, where D is the input size, so that's 784, and L is the output size. So it takes you from D things to L things. Fancy that. Such that in matrix notation, G of B plus W2 is S of, so F of X. Where's X? X is our input vector. Right. We take weights times X plus some bias. We pump those through this wacky function S, which is sort of like our hidden layer here. That's the activation function on the neuron. And then it gets multiplied by W, which is the new weight coming off that neuron, plus the bias going through G, which is our softmax function or our logistic regression, whatever you want to call it. And H being this layer, the S of whatever constitutes the hidden layer, of course. Weights are in D times DH, so the number of inputs times the number of hidden nodes is how many weights you got to worry about, which is a lot. Each column WI represents weights from the input units to the ith hidden unit. Yes. Typical choices for S include tan H. So this is an alternative to the sigmoid function, hyperbolic tangent. Also conveniently differentiable. Or logistic sigmoid, this thing. We're using tan H in this tutorial. Okay, I lied, we're using tan H. Typically yields faster training, and sometimes better local minima. So that's something yet you can explore and play with as you're working with a neural net. All right, output vector thus obtained is this O of X. You should recognize this as a form of, yes, this is the same type of thing that we did when we were classifying digits. We get a vector of probabilities, which is very nice. So to train an MLP, we learned all of the parameters of the model, which is a lot. Oh, I should mention, the thing I talked about, how you actually train these parameters, that's called backpropagation. That's an important phrase you'll see come up quite often. A special case of the chain rule of derivation. There's a whole lot of chain rule from calculus that goes on in backpropagation. If you want to derive it yourself, get real familiar with chain rule. You're going to be using it a lot. because you're sort of doing the error with respect to this thing, and every time you go back, there's another level of chaining involved. So, but it's not too bad. So yes, here we are estimating the hidden layer, we're writing a class to handle the hidden layer. So this is going to be kind of generic. We'll have a nice class. We should be able to just slam one hidden layer into the next if we want to deepen our network for whatever reason. Sometimes that's the right thing to do. One of the catches I didn't talk about, how do you initialize your weights, especially in your hidden layer? You want to make sure that, like, for example, if you initialize them all to 0, you're going to have a bad time. So here they recommend uniformly sampling them from a symmetric interval that depends on the activation function. So uniformly sampled, as opposed to, say, Gaussian or normally sampled, that just means if you had 10 numbers and you uniformly sample them, a 1 is just as likely as a 2, is just as likely as a 3, so on and so on. Every possibility is equally likely. If something's like normally sampled, then the ones in the center are more likely. And there's reasons you might do that, but not in this case. From a symmetric interval, so it's going to be same plus and minus of the same amount. For TANH, they've cited a paper here from, is this on Archive maybe? Well, it's loading up deep learning. Where did it? Xavier 10. No, just understanding difficulty training deep from 2010. Well, that's cool. And they just give us the value. They say, all right, we've computed it. It's this plus or minus square root 6 over fan in and fan out, where fan in is the number of units in the ith minus 1 layer. So in our case, the ith minus 1 is the hidden layer, so it's the second to last hidden layer. Is that right? Let me make sure I get that. Where ith minus I minus 1. A fan out is the number of units in the ith layer. Oh, the number of units in the layer before this layer. So if you have many, many layers, you want to initialize based on the number of units in the layer. I'm going to say above, because I always think of my inputs at the top and my outputs at the bottom. I don't like that most neural net graphs like this I've seen have the outputs at the top and the inputs at the bottom. That's just something that bugs me. I feel like I write top to bottom, I should input things top to bottom. But I guess if you're computing the weights and you're doing the back propagation, you start at the outputs and work your way towards the inputs. So in that sense, it's correct. So that's for TANH. If you're using a sigmoid, you use this other function, which is in fact just 4 times the same thing. So that's kind of cool. In general, you're probably not going to have to, you probably aren't going to have to figure this out yourself if you're using a standard activation function and a typical neural net. If you're doing research on your own, you might. And that would be a good time for you to read some of these papers and how they computed these. And again, we'll be uniformly sampling within this, in this region. And this is square bracketed, so I'm guessing that's inclusive. But we'll see. That might just be their notation. Ensures that early in training, each neuron operates in the regime of its activation function, where information can easily be propagated both upward, flowing from inputs to outputs, and backward. Upward and backward, not like upward and downward. That's just a little confusing. Basically, make sure that your neurons aren't really close to 0 or really close to 1. That they start out at some reasonable values, and if some of them end up closer to 0, hey, that's fine. That's life, you know? All right. What are some other things to pay attention in this class that we're defining? We're going to have a random number generator input. We've got some inputs to the layer. There's a certain number of inputs. Really, in Python, you should be able to infer that. Oh, maybe in Theano you can't. Maybe that's true. A certain number of outputs. You got some weights. And you got the bias. And you got whatever the activation function is. Here, it's Theano.tensor.tanh. And they've got the full doc string right here. Okay, so what do you need to worry about? Well, we need to initialize these W's. That's what we were just talking about, the weights. So we say, if you don't hand me the W's, maybe you already know from another model or something. We say, okay, do whatever your RNG is .uniform. So you have to make sure your RNG has this type of call. The smallest thing is this numpy.square root negative. The big thing is the square root of the positive. The size, this says, what size do you want the array to be? With the array being the ones that we're stuffing into W values. So number of in rows, number of outs. Because we need number of outs weights for every neuron. So that's number of in times number of out. And type, these are floats, float x. If the activation not energy, is a sigmoid, then it's the same thing with tan h with times 4. Note, this doesn't actually check that we're using tan h. This just assumes it, that's okay. Maybe, whoa. Maybe it's okay anyway, it doesn't matter. That might be something we screw around with. We might try some different activation functions. It looks like Theano includes several. Theano.tensor.nnet.sigmoid.tanh. Whatever. Okay, so we set up those actual values, and then we stuff them into an actual Theano tensor object. And this is like assigning them to the graph. It's Theano.shared. So it's something we're going to be changing as we do the computation. And then we do a similar sort of initialization for the b values. Again, we got here we're initializing them to 0. I guess that's considered okay. I'm a little surprised that you don't do the same kind of initialization, but I haven't read this paper, so that could be that. And then we, given the actual Theano object, we make the self.w and the self.b. So they're part of the class. They're attributes of the class. Okay, then what do you actually do with these weights? Well, you take whatever was thrown into your neurons, and you hit them with all the weights, and then you add the b value. So this is like linear output. So that's almost always you start with this, and then you call your activation function on that input. Or output, however you want to think about it. And if you're not past an activation, then they say, hey, your output is just a linear function. That's a completely legitimate activation function. It works good in some instances and not in others. So if you don't pass it that's what happens. Otherwise, it says, hey, call activation of linear output. So activation being that function you passed in, and recall it defaults to this hyperbolic tangent, which has this recommended starting interval. Okay. So that's just a simple activation, the standard neuron stuff. Okay, so that's for the hidden layer class. And then we're going to make an actual class that's going to be a bunch of multi-layer, a bunch of hidden layers and other kind of layers for our multi-layer perceptron, MLP. So in this case, it's got an RNG, it's got inputs, the number of input nodes, the number of hidden nodes. This is going to have one layer, and then a number of output nodes. And so it initializes the hidden layer here with whatever the RNG was, whatever the input was, whatever the number of input nodes is, number of output nodes, and our activation function. And then we sort of got the regression layer here. And so this is why it's sort of like a 2-layer neural net, because we really just define this layer because the inputs sort of come for free, and then the output layer where we run the regression. So you might recognize this from last week. As I mentioned, I did 15 minutes after the video get my thing working. I just had some stupid bugs. Okay, so you define the layers here. We're using that hidden layer function we wrote, and then the logistic regression function that we wrote last week, or that you just downloaded. That's fine too. They're doing a thing called regularization. Let's look at that for a second. We're going to add an extra term to the loss function, so the cost function, which is our negative log likelihood, which penalizes certain parameter configurations. Interesting. If our loss function is this, then regularized loss will be, so we're adding this lambda r of theta, or in our case, lambda size of theta, where theta is the LP norm, so we're doing for L1 and L2. It controls the relative importance of the regularization parameter. Commonly used values for P are 1 and 2. Regularization calls weight decay. Adding regularization term loss will encourage smooth network mappings to a neural network. Oh, so we discourage our parameters from getting too extreme is what we're doing. So we'd rather spread out effects than do it all in one situation. Do it all in one particular value that's just hitting everything. So we're hoping to find a simpler solution than. There might be some solutions that, oh, this gets you kind of a great score on your sort of training set, and then when you do the validation, you find, oh, this was terrible. So that'll help us avoid that problem. I should briefly explain what's called the L1 norm. Means the absolute value of the difference. So if you like to think of a simple plane of x and y, if you want to find the difference between the distance between 2 points, the L1 norm is the absolute value of their of the difference of something. Why can I not for the life of me remember that? Anyway, the L2 norm is what's commonly known as, that's like the square. It's like x minus y value squared. That L1 norm is just absolute value of x minus y. And so you can cube it, you can take it to the 4th power. There's other fancy things you can do. You might recognize the L2 norm is used a lot in regression or in least squares. That's the square part of it, the least squared error. It has a lot of convenient statistical properties, but here we're doing both L1 and L2 regularization. So basically we just compute we say, okay, what's the absolute value of the hidden layer weights plus the regression layer weights? And for L2 we say, what's the absolute, or not what's the absolute value, what's the hidden layer weight squared plus the regression layer weight squared? And so we're penalizing extra large weights, or weights of large magnitude, I should say. And then we do our usual negative log likelihood thing, which is just the regression layer only. The errors that we're computing are always the errors on the final layer, the log regression layer in this case. And what the heck are all of our parameters? Well, it's all the parameters on the hidden layer and all the parameters on the regression layer. If we had additional layers, then we would have more parameters here, and that's something I want to get at. Okay, what is the actual cost that we're going to climb on? Well, it's going to be whatever our negative log likelihood is, plus our L1 regularization. Note that we've got this self.L1, that's this classifier.L1, and this classifier.L2 squared, that's this. What are L1 reg and L2 reg? We'll get to that in a second. Hyperparameters controlling the weight of these. So how important is this to us? How important is that to us? They're going to give it to us later on. Okay, I want to finish this up in just a couple more minutes and then get to actually building it. So gparams, these are gradient parameters. So we're saying, hey, take the gradient of the cost with respect to these parameters for all the parameters in my classifier, so in my neural net. And those parameters are all the weights and the bias weights. So those are all the parameters for gradient descent. So it'll do the derivative calculation for us, spits those out as gparams. And then we say, okay, how do we actually update these? So this is the gradient descent. Okay, so updates. So the param minus learning rate. So the old thing, new thing. Param, we subtract learning rate times whatever the gparam, the gradient of the parameter is. So that's straight up gradient descent. It might be doing something smart. I'll have to double check that. And yeah, and you just say, what are all my parameters? What are all the gradients of my parameters? That's all. And then how do we actually train this model? We have to make a special Theano function, so it will compile. Our inputs, we're going to input an index here because we're going to do a batch of images at a time that we're going to try to look at. So it's like index times batch size, index plus 1 times batch size. This is a common idiom you'll see when going through data sets. If you want to do a chunk at a time, this will give you sort of consecutive chunks, which is nice. And for the train model, we've got index. The output is actually the cost, not the like actual probability of a given digits. I only care what the cost is when I do this. In my update, because that's what I'm going to climb on. My updates are my updates. That's the gradient descent. And the given, I've got a training set in X. I've got a training set in Y. That is, those are the X's are my pixel values. The Y's are the actual outputs, the actual classes. And so putting it all together just sort of grabs all that and makes into one giant file, which I have downloaded already. So it defines this hidden layer and the MLP classes, and then it just makes a function to say, hey, test a multi-layer perceptron with some reasonable values, like this learning rate, this weight for our L1 reg. Notice the L1 reg is actually 0 as a default, and L2 reg is very small here. It says, go, hey, do this 1,000 times. Go through the entire data set 1,000 times. Batch size 20 says, look at 20 images at once. So look at 20 images, see how many errors you had, and update, or see what your cost function was, and then update all your weights at once. And hidden just says, how many nodes are there in our one hidden layer? This is fixed to have one hidden layer. Here's just some setup stuff. We're making our index. This is the X, it's going to hold our inputs. This is Y, it's going to hold our outputs in the actual data set. RNG, we're going to use numpy.random state. This initializes the random state to a fixed value. So if you want to follow along and get the exact same answers, you should use the same random state of 1, 2, 3, 4. Numpy.random is totally fine for our purposes as well. And then we make the classifier, we call that MLP class. With the RNG, our inputs are the X's. And we loaded X's somewhere, didn't we? Oh, that's just interesting. Oh, this uses some globals, doesn't it? Because we don't pass in train set X. That's kind of bad. Oh, no, that's fine. That's fine. Because we're going to say classifier dot with givens. No, that's totally fine. I retract any claim about globals. All right, cost. Well, as I said before, test model. So we'd have the train model is built into the MLP. Test model says, hey, given the index that a particular batch that I'm on, what are my errors? How bad am I? That's all. Validate, same thing, but on the validation set instead of the test set. We do our gradients, we do our updating, we call our train model. This is just some stuff to actually step through the epochs. Patient says, hey, we have to look at least at this many examples. And every time we find a new best model, we say, all right, we're going to look at even more. All right, while epoch less than num epochs, yeah, this just loops through all the epochs. I'm not going to go through that code. And then you just call test MLP. And if you'll notice, on theirs, it takes an hour and a half to run on a CPU at 3.4 gigahertz, of which my machine is not that fast. But I have a GPU, but mine is apparently not working to that level of correctness in terms of using the GPU, I don't think. It was the other day. I'm going to actually kill this. Ding! And of course, because it was in a function, it was doing terrible. But you can see it started here at 10% after one epoch. So after going through all the data once and updating all these weights in these little batches of 20, it had an error rate of about 10%, which isn't that bad, but it wasn't as good as our logistic regression. However, you notice that picks up pretty quick. And we're at 1.98 error rate here, and it hasn't improved in a while. Best on the test error rate is 1.96. And theirs eventually gets down to 1.65. So one thing I want to do is see if my GPU is working properly, because it was the other day. So I want to check that first. Yes, you can see I've been here. Not surprising. Testing Theano with your GPU, yada yada yada. Oh, is this actually updated for Python 3 now? That'd be nice. That would be nice. Just grab all this stuff, pop this in here. None-type object is not iterable. Cute, cute. Usual stuff. X-range is not defined, so it's almost Python 3. Almost. The prints were updated, but not the range. Use the CPU. Why is that? That's a drag. That's a serious drag. Theano RC. Permission denied. Permission denied? What? That's real cute. To dot slash. Oh my gosh. Well, that explains some things. Link dash s dot Theano R. Thing that exists is always what you gotta do first. Download slash dot files dot Theano RC dot Theano dot Theano RC. There we go. All right. Let me kill that. You know what, let me make a new one. One of these days. Ugh. Auto indent off. Okay. And then let me copy this stuff. Because if I have the GPU, that'll be using GPU device. Okay. So that's good. Try in range. Just to double check. Okay, now it's using the GPU correctly. Let's see how much faster this goes. So that had run for like 40 minutes. It was taking forever. It had gotten through 200 epics. There's some one-time setup to actually compile the model. That's okay, that takes a while. I'm going to do some terrible things and mangle this. So we're going to test MLP. We're going to test MLP on our own, though. Test big MLP. Yeah, there we go. So one thing I want to do. No, not big MLP. My MLP. Is this working? Is this working? Hopefully it's making my GPU do some stuff. So I want to see what happens when we have fewer nodes. Just for giggles. Like suppose you only had 50. Can you get a decent model still? Oh, you know what? I don't need to write my own function to do that. Alright, that's taking forever. I don't like that. That shouldn't be taking that long. Test MLP and hidden equals 50. This really shouldn't take forever to do that. And I kind of want to... Right, anyway. In my MLP, there we go. So now it's training. 1 epic, 2 epic, so now it takes a couple seconds on an epic. Probably because I've only got 50 states. 50 nodes. You notice we're very quickly climbing to something that's, you know, better than what we had been doing. So that's nice. Can we activate specific? I want to get some decent visualizations going, because that's really what's going to make these videos a lot more useful to you guys. Learn to program with PyCUDA. That's not what I want to do. I'm looking at using a GPU. That's the wrong place to be looking. Wrong place, buddy. Alright, well that's fine. So you can see that's improving to 4.8% pretty quick. It's getting out of there reasonably fast. Actually, let's say n epochs. Oh, I love that it knows what I'm looking for. Let's just do 10, just so it can go and it can do stuff. Here's what I want to try. I want to try. What if I have a parameter for how many layers I want? Ho ho. NH layers equals, I don't know, 2. And so now I want a certain number of. Now I need to pass in a list of a number of nodes in each layer. So on the first layer and the second layer, so on and so forth. Cool. So that finished at 4.92%. That's pretty groovy. And it ran in 0.58 minutes, that is to say 30 seconds. Alright. If I do the full-on 500 nodes in that middle intermediate layer. Tons of nodes. So many nodes. You're wondering, like, why could I ever need that many nodes? That's almost a node for every pixel. Well, there's certain combinations of pixels that matter in certain situations. That's why. Alright, for the purposes of this, actually, you know what? L2 rig, L1 rig. Be nice. And epochs and H layers. And H layers. Number of hidden layers. 3yy. Alright. No longer number of hidden layers, but this just needs to be. We need to talk about that. Hidden list. And hidden number of nodes in each hidden layer. In hidden layers. Yeah, there we go. So this is getting through. This is doing okay here. Again, it's getting through an epoch every couple of seconds, which is a heck of a lot faster than it was before. So that is super good news. I'm happy with that. Okay, so let's try to add multiple layers with the 18 minutes remaining. That means we have to screw around with the MLP class, actually, doesn't it? Yeah, it does. It does. So, that was dumb. That was real dumb. Alright. Right, because the MLP class itself is the funky object that doesn't, that specifies, hey, you have one hidden layer. So, that was silly of me. Let's make our own MLP class. Let's call it Deep MLP. Yeah. Deep MLP. There we go. So that ran a little under 2 minutes over here. Not bad. And if it took us 2 minutes to do 10 epochs, it would take us 200 minutes. Or sorry, it would take us 20 minutes to do 100 and 200 minutes to do all of the all 1,000 epochs. We did 25,000 iterations. Did they actually do all the iterations in theirs? I think they did, actually. Iteration 2 million something, yeah. So they did 2 million iterations, and they did it in an hour and a half. So maybe I'm not getting a lot of 10.3 epochs per minute. Yeah. So it took them 828 epochs, okay. I don't feel as bad. I'm doing like 5 epochs per minute here. That's interesting, because they're running on the GPU and I'm running on the... They're running on the CPU. And I thought I was doing GPU. I guess they got 8 threads. I don't know. Maybe this is for the reader results section of this page. I don't know. I'll have to double check that. I know it's using the GPU though. Oh well, whatever. It's running faster than it was before. Maybe I just have a slow GPU with not that many cores. That could be part of my problem in life. Multi-layer Perceptron class. So we hidden. So we need not only a number of hidden nodes, but we need n hidden layers equals 1 by default. For the sake of argument, we'll leave this as is. Hidden layers equals hidden layer whatever for whatever I in range and hidden layers. So right, we're gonna make a hidden layer for every single guy, except the first one and the last one are special, you might recall. Because the first hidden layer takes input from input instead of the previous hidden layer. The last one sends output to the output layer instead of its own special layer. So you have to be careful about that. And we're going to try to be general here. What happens when I do range 0? That's fine. No problem at all. And if I say I for I in range 0, it gives me an empty list. Perfect. That's what I want to see. That's what I want to see. So let me say first hidden layer is special. Let's handle, there's a couple special cases. If the number of hidden layers is exactly 1, equals 1, then you do just like we've done before, right? But we'll stuff it in a list for giggles. Else then we make our first hidden layer. Self.hidden layers, and I'm going to be a terrible person and append to layers because I'm a terrible person. That's okay. So we're going to grab this layer. It's going to be mostly the same, but not exactly. RNG, it's still taking input. So first hidden layer, take whatever RNG, it's going to take whatever input is, it's going to take whatever output is. The n output is in fact the number of hidden, but it's the number of hidden for that layer, right? So the output is the number of hidden for 0 still. And activation equals, sure, tan.tanH, that's fine. So I guess this isn't any different so far. And out equals n hidden out. You know what? All right, sure. I don't need to handle that as a special case yet. Okay. So we initialize it. We're going to have a list of hidden layers. And then I say remaining layers. Remaining hidden layers, I should say. For I in range. And hidden layers -1. So if we have only one hidden layer, this does nothing. If we have 2 hidden layers, you know what? Range 1 does give us something. Range. If I call a list on that, then I can find out what it gives me. Yeah, there we go. I appreciate that range is an iterator, but when I'm working interactively, it is often a source of annoyance when I actually want to see the list that something gives me. So this, we're going to say self.hiddenlayers.append, and we're going to add a hidden layer that's almost the same as this one, but not quite. Again, this is to make a neural net with lots of layers, because that's what we're all about. More layers, more layers. Its input is not input. its input is going to be self dot hidden layers of I. Right. Actually, in order to not go crazy, we're going to start at 1 and go to end hidden layers. Right? That's what I want. Because if it's 1, 2, then I get something if it's 1, 1. And it's nothing. Okay, good. So this way, I want to type I minus 1 here because I'm doing the previous layer. I could start my range at 0 like a normal person and then just keep I, but then I'm going to get real confused and get all mixed up. The number of inputs to this layer, so their input, what's going to this layer, is whatever the output of the previous layer is. The number of inputs are whatever the number of previously hidden things are. And the number of outputs are however many outputs this layer has. And we just do this for every extra layer that we have. And then, in our log logistic regression, we say, give me the last layer, whatever the hell it is. Grab its output and do things to it. Same, it's got that many output things. Our regularization. Dot hidden layers. All right. HL. We're going to say sum of these things for HL in self dot hidden layers. There we go. So we're adding up all those. We're ready to play the same game here. HL sum of for HL in self.hidden layers. So again, we're just changing up our code a little bit so we can handle an arbitrary number of hidden layers when we create our class. Negative log likelihood, that's the same. Errors are the same. Params. Right. So what if I say this? What is params of a hidden layer is going to be the question. HL.params for HL in self.hidden layers. Okay, that looks pretty good. I don't know if this is actually going to work, but it should. It should be fine. Adding to a list, if it's not actually a list itself, could be trouble. But I think params is probably a list. We'll find out. We will find out. Or maybe I can sum them. If I can add them nominally, I might be able to sum them. Okay. And our input is just input. So that's all. And then I don't want to screw around with test MLP. I want to screw around with test with my MLP, right? Where is it? There we go. Test my MLP. So n hidden 25, 25, number hidden layers 2. All right. As usual, I'm about to finish up, and which means I'm about to totally screw this up. Deep MLP. N in n hidden. Yeah, n hidden equals n hidden. N hidden layers equals n hidden layers. That actually probably belongs here. All right, let's hang on here. Hang on. N hidden layers, right? Oh, and H layers. All right, let me call it hidden layers properly. Keep things consistent. And we're going to find out how many bugs I introduced. Few minutes left, And this is all to make it as deeper even. Sometimes deeper is better, you know? Not always, but sometimes. Updates. We got to update just all the parameters. Yeah, it'll compute all that for us. All right, and I'm saying 25, 25 because, hey, why not? Deep MLP. All right. That sounds like fun. N hidden layers. Let me just double check. N hidden 0. Like N hidden should always have an index to it now. Okay, well, let's comment this line out. We ain't doing that anymore. We're testing my MLP now. Oh boy. All right. Place your bets now on how quickly this crashes. I'm betting that there's a stupid thing I missed at least one of. Let's find out. Loading data. End hidden layers is not defined. Boom. That's the first obvious problem. And this is in my actual test function, isn't it? Test MLP. I can't spell. Cannot convert object, yada yada yada. Is this, where is this? Alright, so this is an interesting error at least. N hidden layers equals N hidden layers. Activation equals t.tanh. Yeah. And your output is this. AB. Convert main.hidden layer at whatever to tensor type class main.hidden layer. So it's like it has a pointer and it wants the actual object kind of thing. So this is in my MLP, line 250. And if I can't fix this in a few seconds, I'm going to pause the video and we'll come back to this next week. That's not a problem. So this really shouldn't be part of the problem, right? And out is however many hidden things I have in this layer, right? So we've got 2 layers. Like, I would have expected the parameters to... I would have expected to get burned on line 287 here. That's where I would have expected to get burned. All right. You know what? Cannot convert class as tensor error. Cannot convert ents to tensor type. Interesting. So it just doesn't like my activation? Or it doesn't like... Oh, it doesn't like my hidden layers appending to. I see. That's kind of odd. Hidden layer. Do I use a single hidden layer anywhere? I don't think I do. Oh. Could be problem in that the list in Python kind of holds a reference to the object. And I kind of need that object to be like purely in the realm of this class. Which is still a little frustrating. That is the way how it's complaining about this. So I suspect the real problem is on like this input. It's telling me it's on the activation just because that's kind of where it's done doing stuff. But if I move activation up here, for example, because I've named all my inputs, so it doesn't matter where I put it, will it still choke on activation? No. See, now it chokes on whatever the last line there is. So it's not really a problem with the activation. So it's important not to be fooled by that. That's just, oh, the last line where I'm doing this hidden layers.append. So it can't make a hidden layer out of this thing that I've passed it. I'm betting it's really a problem with the input here. Right. because it should be this dot output. Right. I'm not passing the layer itself in. I want to pass the output of that layer in, just like in the log regression. So that was my own fault, my own dumb fault. Building the model. Hey, you can't multiply sequence by non-int. This is almost certainly a problem with my list of parameters. Let me turn on PyDB. Python debugger, which is super great. What does param look like? WBG param? So that's kind of like, I want a specific parameter there. All right, now this seems like a solvable problem. So normally I just have a bunch of params, right? Like, what is W? Well, W is whatever. Param 0 plus param B. What does that mean? Oh, sorry, param. Oh, jeez. Param 0 plus param 1. That's what I mean. Yeah, so hang on. What are my params? Params. Hidden layer? Where am I? I'm at 615. I don't have the hidden layer. Right, so I'm not adding my parameters correctly. So let me throw a sum around these. And see what happens. Like, I want to flatten those out, is sort of what I want to do. Oh, I didn't like that. Didn't like that at all. Unsupported operand type int and list. Yeah, not surprising. Not surprising. Alright, you know what? Let me... Like, this feels like a solvable problem. It really does. Close that. I always tell myself I'm going to be finished, and I don't. I go overtime, but that's okay. No one from chat here to save me this time. Oh well. This is what you guys are here for, to see me fail pretty miserably after almost. This is almost working, I promise. It's just like just a syntax thing of how do I join all these parameters. Theano layer parameters. Maybe that's what I need to search for. Theano layer parameters. Oh, you know what? Actually, I have a good idea. We're going to do this. We're going to say that. And then we're going to say for params in for HL self dot hidden layers self dot params plus equals HL dot params. Maybe this will work. So now I'm no longer adding this list. I'm adding each one at a time here. Don't joke. Oh boy. Refreshing luck. Okay, whoa. Oh, this looks like maybe it's working. Maybe it's doing something. Hey, it's working. What do you know? And it's doing about, maybe one batch a second or something like that. That's actually working, and that's climbing down pretty quick. Look at that. Only 5 extra minutes, and we are in fact training a model. 2 hidden layers. More than they have. And now we have a function that can handle an arbitrary number of hidden layers. So that's pretty cool. That actually worked. I want to let this run. Crap, how many times have I letting this run? I think this might be doing the full 1,000. Look at how quickly this is. Look at this. Look at this. Check this out. 4%. 4.5%. That's pretty quick. We had gotten down to 2% eventually with the previous model. But this is going quick. This is good. And this is with 25 nodes on each layer. Look at that. Boom, boom, boom. Validation error, 3.some%. So this is kind of cool. Now I'm stoked. Now I'm in a good mood. That actually worked. We did some simple Python. to change the Theano tutorial code from one hidden layer to two hidden layers. So if we go back to their image here, we have an extra hidden layer here. So the outputs of one hidden layer feed into the next layer. And you might be thinking, well, that's kind of dumb. It's already a universal approximator. But it might end up making more sense. Sort of each layer is often thought of as like a certain set of features. And if you feed those features into something else, you can often extract like yet different features out of them. Because maybe, oh, these two features together go together and they do something like this. We'll get into that more, and more specifically when we look at convolutional neural nets. That's sort of where you like specify that up front. You say, this is definitely this like particular part of the image. So we'll get to that when we get to that. All right, but that was kind of cool. And now we have a basic building block for doing neural nets in Theano, which is pretty nice. All right, we didn't get any cool visualizations, but maybe that will come. I think that's all we got for this week. Our model is still going. I might let that run a little bit and let you guys know when it gets to. Hey, and let me know if you are playing around with Theano on your own. Let me know what you do, or if you do something different with this. Send me an email or post on the YouTube page. Go to my webpage. I'm on Twitter now. You can annoy me at DanDoesData. Have all kinds of fun with that. All right. So you guys have a good time and have a good night.